Your problem 6, which would be the last problem on the test, will be a centroid and moment of inertia problem. We have a T section here, and normally what I would do is I would break it up into two rectangles like this. But to increase the degree of difficulty, and actually to do something that I do in my reinforced concrete classes, I broke it up like this. And what's interesting is you have the regular red rectangle, and then you have these two green ears. Well, the two green ears can be added together as one rectangle. Okay, so the green adds up to something that's 250 millimeters wide and 50 millimeters tall. To further add to the difficulty, I picked my coordinate system, my temporary coordinate system, before I calculated the centroid, to be right at the centroid of the red rectangle. Okay, right at the middle of the rectangle is where I put mine. I think a normal way to solve this would be to put the temporary coordinate system at the bottom of the beam or the top, bottom right there, or at the top. But I did it like this in class so that I'd give you the opportunity to redo this exact problem like this, how you would normally solve it, to see if you got the same exact answers as I did. And if you could do that, you can know that you got it right. I mentioned in class that the problem on the test will be made up only of things that are on that practice sheet. Not the practice sheet, that are on the back cover of the book, which you'll be given. That means you won't have to do any integrals on the exam. Okay, to get the centroid, you just need sum a times y divided by sum a. And what you do is you set up a table, you get the area, you get the y, and then you multiply a times y. The area of the red rectangle is 15,000 millimeters squared, and the area of that green rectangle is 12,500 millimeters squared. Given my unusual choice of coordinate system, temporary coordinate system, I put it right at the centroid of the red rectangle, so the distance from my coordinate system to the centroid of the red rectangle is 0. That's convenient, so a times y is 0. The distance from that coordinate to the middle of the green rectangle was 125. You can look at the picture and see that. And if you take 12,500 times 125, you get this 1.56 million. You add them all up, there's the area 27,500, and you add them all up, you just get the 1.56 million. You take sum AY divided by sum A, and you get 57 millimeters. So the new centroid of overall is 57 millimeters above the centroid of the red rectangle. Adding the green ears moves the centroid up 57 millimeters. And this kind of makes sense. The distance between the two individual centroids is 125 millimeters. Half of that is 62.5. The red rectangle is a little bigger than the green rectangle, so the centroid should be slightly closer to the red centroid, so less than 62.5. So 57.8 seems right. And I did double check it with Excel, and it is right. Okay, so that was the centroid part. Next is the moment of inertia. And what we're going to use is a parallel axis theorem. You get the moment of inertia about your own axis, I0, and then you take AD squared, where D is the distance from the overall centroid, which we just calculated, 56.8 millimeters above the centroid of the red. The distance between the overall centroid and the individual centroids. Okay, the area of the rectangle was 15,000 and the area of the green rectangle was 12,500. The moment of inertia of a rectangle is 1/12 base times height cubed. So there you go. And 1/12 base, you could take that 125 and 125. as the entire base, so 250 times 50 cubed, because it's 1/12 125 times 50 cubed plus 1/12 125 times 50 cubed, which is 1/12 250 times 50 cubed. This is a part I really want to slow down and explain. D. D is a distance from the overall centroid to the individual centroids. So if you look at this picture, the distance from the overall centroid to the red centroid is this, which we just calculated. It was 56.8. It's actually minus 56.8. It's going down. Okay. And the distance, the green distance, is the distance from the centroid, overall centroid, to the centroid of the green rectangle, which is 125. We just said that 125 was the distance between the coordinate system and the green centroid. The overall centroid is 56.8. This distance here, that's what we want. If you look at the picture, you can see it's 125 minus 56.8 right here. This comes out to 112.5 million. This comes out to 2.6 million. That comes out to 68.2. A times D squared comes out to 48.4 million. A times D squared is 58.1 million. You need to add up these four numbers here. I0, AD squared for both of them. If you had three pieces, you would have six numbers to add up. And I added up the columns first, so the two I0s add up to 115.1 million, and the two AD squareds add up to 106.5 million, and then when you add them both together, you get 221.6 million millimeters to the fourth. Really, you just needed to add those four numbers to make it easier. I just added columns. You might have in a real problem, not on the test, you could have like 6 or 7 pieces, and then it makes sense to add the columns up than to add the rows at the very end. And I redid this thing on Excel, and it's actually 221,638,258 millimeters to the fourth. Please, I would only like 3 to 4 significant figures, so 221.6 million millimeters to the fourth. And as said in class and as written here, friction problems are not on our final. I will solve these, and I will record some friction YouTube videos for you to enjoy over the summer if you like, or maybe better, review just before you get to that part of your dynamics class, and then you'll have that ready to go. It's actually kind of a pity that we don't have friction on our final. We just were about a half week too short on time, because when I gave this exam in Hawaii, this problem, the friction problem, actually had the highest average of all 6 problems. But I didn't want to add confusion. We had not really gone over it in class and really didn't have a homework on it, so it's not on our final.